Good morning, class. We are looking at chapter 2 limits. Here's 2.5 continuity. So we covered limits of sequences, limits of functions at infinity, limits of functions at finite numbers, limits, algebraic methods, and we are going to move on to continuity. So to refresh everyone's memory, we looked at limits of functions at finite numbers, numerical and graphical approach. And now here's a basic definition. Limit of f of x as x approaches a equals L. This is how we read that. And reminding you that when the limit of a sub n as n approaches infinity is L, we say that a sub n converges to L. When the limit of a sub n as n approaches infinity is infinity or negative infinity or dne does not exist, we say the sequence diverges. And to find limits, simply we plug in an opposite. Here's an interesting example. We want to compare and contrast all three functions. And so we want to take the limit of f of x as x approaches a. So here's a. So coming from the left and right side of a here, that means this is from the left going from the bottom. This is from the right going from the top. In all cases, we are moving towards this point. So along the y-axis, coming from the bottom, coming from the top, we are moving towards L, and the limit exists, and the limit of f of x as x approaches is L for this function. Same thing for this one. Same thing for this one. The limit of f of x as x approaches a is L with respect to all of them. What's the difference? This one, f of a is also L. This one we see a whole, a discontinuity. So f of a has a different value than the limit b. This one, we don't have a solid point. F of a is not given to us. It's undefined. So part A, f of a equals L. Part B, f of a equals B, which is not equal to the L. Part C, f of a is not defined, but in each case, regardless of what happens at A, the limit of f of x as x approaches A is equal to L. Definition of a horizontal asymptote is as follows. When we take a limit of f of x as x approaches negative infinity or positive infinity, and we get to L, the line y equals L represents the horizontal asymptote, everybody. The line y equals L represents the horizontal asymptote. When we take the limit of f of x as x approaches a, or a from the left, or a from the right, and it results in negative or positive infinity, then VA, vertical asymptote, has the equation x equals a. And as far as one-sided limits are concerned, the limit of f of x as x approaches a from the left equals L. The limit of f of x as x approaches a from the right equals L. Then we say the limit of f of x as x approaches a exists, then it's equal to L. In other words, the limit only exists when the one-sided limits are identical. So that's the synopsis of what we covered. And now continuity, 2.5 continuity. Here's the definition. If function f is continuous at x equals a if the limit of f of x as x approaches a equals f of a. Meaning, number one, f of x exists. The output at a exists, the y coordinate. The limit of f of x as x approaches a equals L, that exists. The limit as x approaches a exists, meaning one-sided limits are identical. And this limit of f of x as x approaches a, and this functional value f of a are the same. The limit is the same as the output. That is the definition of continuity. A function is continuous over an interval I if it is continuous at each point A in I. If f is not continuous at x equals a, we say that f is discontinuous or has discontinuity at x equals a. The concept of a direct substitution property has been discussed. A continuous function at a has the following limit value. The limit of f of x as x approaches a equals f of a. And finally, functions with the direct substitution property are called continuous at a. Let's start with a simple example. So again, reminding everybody about the definition of continuity, limit of f of x as x approaches a equals f of a. This is the definition of a continuity, and a one-sided limit. It exists if both sides, limit of f of x as x approaches a from the left and right, are identical. Now, for this function, and the graph is given, at which numbers is f of s discontinuous and why? So we're going to go from left to right from the very first one. Number 1. So at a equals 1 or x equals 1, the function is discontinuous. Why is that? If you look at this, we do not see a functional value. We don't see a solid point. F of 1 is not defined. What about the limit? Just for the sake of argument, as we approach 1 from the left or from the right, in both cases, we are moving towards this point, which has a y coordinate. One, so the limit of f of x as x approaches 1 is fine, exists, it's equal to 1. But f of 1 is not defined. The next number, anybody can see what else we don't have a continuous function? Discontinuity takes place at what other point?
3.
Very good. At number 3. So let's see what's going on with a equals 3 or x equals 3. At that point, I hope you see that the limit of f of x as x approaches 3 does not exist. So that would be the end of it. However, just to elaborate on that and make sure everybody's comfortable with the concept, what are the limits? What are the limits from the left and right? So what would be the limit of the function as x approaches 3 from the left? Anybody? Three from the left. From the left of 3, we are here. We are moving towards this point, and this seems to have the answer -1. What about the right side of number 3? We are moving towards this point, having y coordinate 2. The two limits are different, therefore the limit does not exist. Then the limit of f of x as x approaches 3 does not exist. Again, just to make sure we have mastered this, can anybody tell us what is f of 3? At x equals 3, look for,
Does not exist.
no, it does. F of 3 exists. Look for a solid point. Do you see a solid point? This one.
-1.
Excellent.
-1.
So the answer is the y coordinate of the solid point. So this is equal to -1. So again, f of 3 is also defined. Now, of course, just for the sake of argument, because these two are the same, right? That means the function is discontinuous at 3, but it is considered continuous at 3 from the left. Continuous at 3, that's the meaning of it. Continuous at 3 from the left. There is one more point, and that would be number 5. The function is discontinuous at a equals 5 or x equals 5. Why is that? Because the limit of f of x as x approaches 5 is not equal to the f of 5, the functional value at 5. Let's see if we can see why. As we approach 5 from the left and from the right, we are moving towards this hole. And this hole has a y coordinate 1. So the limit exists, yes. The limit of f of x as x approaches 5 is equal to 1. But it's not equal to f of 5. Class, so what is f of 5 equal to? Anyone?
3.
Perfect. So f of 5, look for a solid point here. Here's the solid point. What is the y coordinate of solid point? 3. So this is equal to 3. They are not equal. That means discontinuity. If you pay attention to this question, you get a lot of information about understanding the concept of a limit, functional value, and so on. Let's look at this function. G of x is defined as half of x plus 3 for x less than -2, and x minus 1 for x larger than or equal to -2. This is an example of a piecewise defined function. Is g of x continuous at x equals -2, y or y not? First of all, why are we interested at x equals -2? If you look at the top piece, this is a linear function. The domain for any linear function is all real numbers. So this function is continuous from negative to positive infinity. Therefore, it's continuous from -infinity to -2. This function is also a linear function. It's continuous from negative to positive infinity, all real numbers. Therefore, it's continuous in the given interval of -2 to infinity. The only thing we need to check is the endpoint, namely -2. So we have to look at 3 things. We're going to look at the functional value, the left side limit, and the right side. The functional value, that means find the equality. The equality is here. So we have to evaluate this function at x equals -2. So we're going to write g of -2 is x minus 1 such that x equals -2. This is how we write that. Is the notation in math. This line segment is read such that. So plug in -2 and you get -3. Let's look at the limit from the left. That means limit of g of x as x approaches -2 from the left. So because this is less than, this is the function we're going to evaluate. So we're going to evaluate half of x plus 3 at x equals -2. Plug in -2. The product of these two is -1 and 3 is +2. Let's look at the right side. The right side, you're looking for x larger than -2, which is this piece. So you're going to evaluate this piece of the function at x equals -2. So the limit of g of x as x approaches -2 from the right would be evaluating this function at x equals -2. Plug in, you get -3. So it's pretty straightforward, everybody. So what happens is the limit from the left and the limit from the right are not the same. The limit of g of x as x approaches -2 does not exist. So the limit of g of x as x approaches -2 from the left is not equal to the limit of g of x as x approaches -2 from the right. Therefore, the limit of g of x as x approaches -2 does not exist. Therefore, g is not continuous at x equals -2. Something interesting. Notice this number, which represents the functional value, is equal to this number, which is the limit from the right. They are identical. So therefore, g of x is continuous at x equals -2 from the right. We say the function is continuous because of the right side limit. G of x is continuous at x equals -2 from the right. So the answer is yes. Okay. Why? These two numbers are identical. Let's look at types of discontinuities. If you look at this function, there's a discontinuity here. You have a rational function, but when you graph it, you get a hole in a line. You have the same rational function, you have the same line, but at the same time, f of 2 is defined to be 1. So these are removable discontinuities. Parts A and C, removable discontinuities, we could remove the discontinuity by redefining f of x at just the single number, in this case 2. So how do you do that? First of all, when the whole appears because there is a common factor, remember, in order to find the vertical asymptote, you set the denominator equal to 0 and x becomes 2. This is not having a vertical asymptote. Why is that? When you do the factoring, x minus 2 and x minus 2 cancel each other. So this becomes x plus 1 under the condition that x is not equal to 2. Therefore, x equals 2 is not a vertical asymptote. So what happens at 2? If you plug in 2 here into this line, everybody, because this is a continuous function, this is a line. If you plug it in here, it gives you 2, 3, which is the location of the hole. And if it's hard to see the hole, There is a hole here, okay? This hole has coordinates 2, 3. So all we have to do over here, if we define this as 3, then the hole will be covered and there is no discontinuity. That's why they call it removable discontinuity. However, these two can't be fixed. The first one is called infinite discontinuity, referring to vertical asymptote or vertical asymptotes if you have more than one. And this is referred to as a jump. More specifically, this function, double brackets, is called step function. And there are many jumps. However, even one jump, there is no way to fix this. There is no way to fix this, but these two are fixable. In this case, although at x equals 0, the function is undefined, we have given it a function value 1, but there is no way to fix the discontinuity. And that's the idea. Removable discontinuity, vertical asymptote, or infinite discontinuity, jump. Let's look at this example. H of x is h of x continuous at x equals 3, where h of x is defined as x squared minus 9 over x minus 3 for x not being 3, and h of x equals 7 for x equals 3. So why are we looking at x equals 3? If you look at this function, this is a rational function. As you know, every rational function is defined in its entire domain, and it's continuous in its entire domain. And the way you find the domain, you set the denominator equal to 0 and exclude that. That's why they wrote x can't be 3. So all real numbers except 3. So what happens is at x equals 3, they have defined it to be 7. So this is the functional value. But if you want to take a limit, you have to take a limit of this expression. And I hope you remember what you do. You just plug in, and obviously when you plug in, you get 0 over 0. And remember, the 0 over 0 is called indeterminate. Okay. And I said indeterminate to me means more work. That means you use your algebraic techniques. This is in the form of a squared minus b squared, and it can be factored into a minus b times a plus b. So your technique is factoring, is factors into x minus 3 and x plus 3. And therefore, we can cancel out the x minus 3. And now if you take the limit of x plus 3 as x approaches 3, simply put, you get number 6. So we found the limit. Does the limit exist? Yes. What is it equal to? 6 from both sides. What is the functional value? It's given as 7. H of 3 is given as 7. Are they the same? No. Because the limit of h of x as x approaches 3 is not the same as h of 3, it becomes discontinuous at x equals 3. So what happens is that the limit of h of x as x approaches 3 is 6, which is not equal to h of 3 equals 7. Therefore, h of x is discontinuous at x equals 3. All right. I'm going to assume when we went to the breakout room, we know what we have to do. And anybody has the answer for this one? What did you do? What did you get? You just plug in. This becomes 0, this becomes 3, this is 6. square 36 minus 7 times 6 minus 42 plus 12, and we get 3/6 or 1/2. What about here? Anybody want to share with us anything?
You get 1/9.
Excellent. What is this called? What is the name of this? First of all, if you plug in, you get 0/0. This is called a complex fraction, right, class? So you have an indeterminate form. You multiply the top and the bottom by 3x, which is the LCD. And you don't touch the denominator, you keep it as a product. And when you multiply 3x by the top, you get x minus 3. We can cancel those. We get the limit of 1/3x as x approaches 3. Then we replace it. We get 1/9 as the final answer.